So today is the last lecture for this first part, and then you will have a, I think, 1 week break, and then Professor Solidoro will start with the other 6 lectures, mainly covering the ocean biogeochemical cycles. So today we'll finish with, by talking about aerosols, and in the second part we will discuss about the interplay between climate and air quality, and as well a few examples of air quality may affect the ecosystem functioning, and as well how air quality and land use change may interconnect, may be linked. But let's start talking about aerosols. So just as a short introduction, what are aerosols? So let's try to define this component of the atmosphere that is called aerosols, or as well particulate matter, so the acronym PM. So it's a mix of solid and liquid particles that are suspended in a gas phase, the atmosphere. They have a size, they are very tiny particles with a size that span from few nanometers to 10 to tens micrometers. So compared to cloud droplets, they are quite small because cloud droplets can grow even more to hundreds of micrometers. But the most important thing is that they are a multi-phase system. So in an aerosol, we can have the solid, the liquid, and the gas phase. And so this explain why it's so difficult, why it's so complex to study aerosol and as well to reproduce aerosol with models. Because we have to follow the three, we have, for example, to take into account the equilibrium between these three phases. With an aerosol, we may have different chemical compounds that are in the composition of the aerosols, and so they will influence the chemical reaction that can occur between the aerosol and the surrounding environment. And so because of this multi-phase system, I'd like to stress that today's lecture is really a brief introduction about aerosol. The science on about aerosol is broader. It's broader than today's lectures, and if you are going to study aerosols, you may need to delve more into the chemistry that is involved, the physics that is involved. So today we are I'm just trying to provide you some general information. Aerosols can have different sources, from natural to anthropogenic sources. Here we are looking at a global map of the aerosol optical depth, so the extinction of radiation that has gone through an aerosol layer, and so has been reduced due to the presence of these tiny particles that can scatter the light or absorb the light depending on their composition. And so here we can distinguish already some natural and anthropogenic sources. So for example, as natural, we have desert dust, for example, close to Sahara, or wildfires over Alberta. And then we have as well anthropogenic sources of aerosol coming from fossil fuel burning, biofuel burning for cooking, domestic heating, and biomass burning, for example, agriculture fires to prepare the land for croplands. And why do we care about aerosols? Well, for many reasons, going from air quality to chemistry to climate, and going more into details. In fact, aerosols, for example, in terms of air quality, we have already discussed their effect on acid rain. When we introduce the pH of a solution, we know that the pH of water is 7 in a pure water system, but then natural rain has a mildly acidic pH because of the presence of carbon dioxide, and we have seen that as well there are some other acid components as sulfuric or nitric acid, or as well some base component as ammonia that can shift the natural pH of water. And so aerosols are involved in the formation of acid rain. They may as well change the visibility. They can affect public health. They are involved in climate. We are talking in a moment about this. They can also affect the ozone chemistry because of some heterogeneous reactions that can occur on the surface of aerosols. We will see this today. And for example, if you remember, while talking about ozone chemistry, both in the stratosphere and in troposphere, we talk about photodissociation. In the stratosphere, the photodissociation of a molecule of oxygen is the first step in the Chapman mechanism to produce ozone. So it requires photons to split the molecule of oxygen, and as well in the tropospheric chemistry, we have seen that the photodissociation of ozone produces the hydroxyl radical. If we have a layer of aerosol, you can imagine that part of the incoming radiation is filtered out, so it can reach the lower layers of the atmosphere. And so since the number of the photons determines the actinic flux in the photolysis rate constant, then the presence of aerosol can change the photolysis rate and can change the photodissociation process. And as well, aerosols are also involved in biogeochemistry because they can, for example, lead to ocean fertilization, or as well through the aerosol uptake by plants. Some nutrients can then be uptaken by living organisms as plants or phytoplankton, etc. Looking more into the details of aerosol effect, here I chose to show you, for example, the effect of aerosols on human health, focusing on the respiratory system. Here on the left, we have a representation of the respiratory system that we decided to split into three parts. The upper part going from the nose to the larynx. Then we have an intermediate part involved with the trachea and the bronchi. And then the deeper part of the respiratory system where we have the alveoli. And if we now look at these plots on the right, we see here what is represented is the deposition of aerosol given as a percent, that is given as a function of the size of the particles that reach the respiratory system. So if we focus on the upper part of the respiratory system, we see that mainly the larger particles are already stopped there. The position is quite efficient for large particles in this part of the respiratory system, although we have as well a high percent of small particles that can be already stopped there, for example, due to the mucus that is present in the upper part of the respiratory system. While if we move deeper in the system, we see that in the intermediate and the deeper part, we don't have any more a lot of large particles that can reach this area of the respiratory system. We have more fine and ultra-fine particles that can go deeper in the respiratory system. And so if aerosols that are stopped there can just cause, for example, throat irritation or just coughing. Here, the issues is that where you have the alveoli, what happened there is the gas exchange between the carbon dioxide that is ejected by the body and the oxygen that is uptaken by the body. And this involves as well exchange, this gas, the oxygen is then released in the blood, in the cardiovascular system. So it can then be transported everywhere to all the organs in our body. So if an aerosols can reach this part, it can then it won't stay just in the respiratory system, it can then be transported elsewhere, and it can have some more hazardous effect on the human health. And then another effect of aerosols is related to visibility. We have already discussed about this during the first lecture where we introduced partial pressure. Here we are looking at the PM10 concentration, mass concentration, over 1 month over Beijing in 2008 during the Olympic Games. And as you see, with the increase in the mass concentration of aerosol, we have as well a drastic decrease in visibility. And this can affect, for example, the functioning of some infrastructures, as airports, highways. And so, for example, when you have a wildfire that bursts out close to a highway, then you may have that infrastructure need to be stopped because of a reduction in visibility. And then we have as well the aerosol effect on climate. But here I stopped. Have you already discussed about the direct and indirect effect of aerosols in other courses? Yes? Maybe with, have you? No. I have just 2 slides, so it will be really short. If you have already seen, it's not a problem. But so, aerosol can have a direct and an indirect effect on climate. The direct effect is mainly related to the fact that aerosol, depending on their composition, that can be scattering aerosols, for example, sulfate or organic aerosols. And so they have mainly a cooling effect on climate because they reduce the amount of solar radiation that can reach the surface and warm the surface. While there are some other aerosols, for example, desert dust, they can absorb the radiation, and in this way they can warm the climate, they can have a warming effect on climate. And so scattering and absorbing aerosols are involved in the so-called direct effect on climate that mainly influence the temperature of the Earth system. While the aerosol indirect effect involves a change in cloud formation and cloud properties. As I'm sure you know, to form cloud droplets, you need some aerosols, because on this solid particles, what happens is that cloud droplets can stick on them and then can grow, and so we need this so-called cloud condensation nuclei on which cloud droplets can condense and form and grow when relative humidity allows this, when the atmosphere is oversaturated, and so the cloud droplets can form. Now let's try to compare 2 conditions. One is we call this a clean, pristine atmosphere where we have few aerosols, and we compare this to a polluted situation where we have many particles that are dispersed in the atmosphere. So in a clean environment, what happens is that we have cloud droplets that can form on these few particles, and so we have finally an efficient system in terms of precipitation with a low albedo. Instead, if we are considering the same system with the same atmospheric condition, but we have more particles, what happens is that the same amount of water has to be shared between many particles. And so finally, we ended up with smaller cloud droplets, and so they will be less efficient in precipitating, because you imagine as well their weight, the gravitational effect will be lower, and as well we will have thicker clouds with a higher albedo. So in this way, by having more and more, in this way, aerosol, through this so-called indirect effect, they influence climate because they can change, for example, precipitation and as well the albedo of the Earth system by changing the cloud albedo. So now this was just a short introduction, just to introduce what are aerosols and what are their effects on the health, on air quality, on climate. Now we start introducing, we start talking about aerosol, how aerosol can be formed, and it's very And as well, we will start introducing the different way we can classify aerosols. So, in terms of how the production of aerosols, we have two ways. One is, and this already introduced the first classification of aerosols. Aerosols can be primary aerosols. They are emitted they are mechanically produced by, for example, the action of wind over the sea surface, and so we have sea salt spray, or as well over desert, so we have soil dust. So these primary aerosols belong to the also called coarse fraction aerosols, because these particles at the size between 1 and 10 micrometers. So they are the largest particle in the aerosol, in all the aerosol group. And so they can interact with cloud droplets, as we have seen for cloud condensation nuclei. However, the main way they can be removed from the atmosphere is through the direct uptake by the land surface, by tree leaves. And so dry deposition is the main sink for these primary or coarse aerosols. And then we have what we call the secondary aerosols. So we call secondary because the aerosols are not emitted directly as aerosol has in this case, but they result from a gas-to-particle conversion. At the beginning, we have the emission of some gases that are then oxidized, and we ended up with some precursor gases, as for example, sulfuric acid or ammonia or other organic gases. And these gases, they go through a first process, nucleation, where gas molecules started to clustering, to gathering together and to grow. And so we encounter the first, after this first process, we have the production of an ultrafine fraction of aerosol, where particles are very tiny. They have a diameter smaller than 0.01 micrometers. But then, depending on the condition on the environment, this ultrafine aerosol can still go on growing through two other processes called condensation, so the condensation of gas molecules on pre-existing aerosol, or coagulation, so the collision between two molecules. And so now we move from the ultrafine to the fine, or also called accumulation mode aerosol, where the size of the particles is a little bit bigger, between 0.01 and 1 micrometer. And this fine aerosol can then interact with cloud droplets and can be scavenged. They can be removed from the atmosphere through wet deposition. They can be scavenged by rain, or also the cycle can loop in this way through as well evaporation if temperature, relative humidity are changing. And so from cloud droplets, we go back to the fine aerosol fraction. So we can, depending on the process that leads to the production of aerosol, and as well the process that leads to the loss of aerosol, we can classify this particulate matter in different ways. So in terms of fraction, you may find one classification that mainly divide aerosol into the fine and the coarse mode, and the coarse fraction, where the threshold is a diameter of 2 micrometers. If you may find as well this classification made on aerosol modes and the process that leads to the creation of aerosols. So we have the nucleation or Aitken mode for the ultrafine fraction, the accumulation mode for the fine fraction, and the coarse mode for the larger particles. And then depending on which mode these particles belong to, also the loss processes are different. For the nucleation or Aitken mode, the main loss processes is through coagulation, so the collision with large particles. For the accumulation mode, the main loss process is wet deposition, is the scavenged by rain. And for coarse mode, the main loss process is sedimentation. And then as well, as we mentioned before, also the source process leads to another kind of classification, distinguish primary and secondary aerosols depending on how they have been produced. And in general, for aerosols, a general lifetime is between 1 to 2 weeks. Then for sure it depends on the weather condition that you have that may influence, may fasten some loss processes, and as well the environment where, for example, the precursor gases have been emitted. And the size of aerosol can also change, as I mentioned, depending on the weather conditions. And one of this is the relative humidity of the environment where a particle is released. So here we introduce what is called the Raoult law that mainly define, I prefer, I write here. So we can think so this is the general form of this Raoult law. Here we are looking at this law for water vapor, and we imagine two conditions. One is water vapor over a surface of pure liquid water, and another water vapor over a surface where we have a solution with a solute that in this case are these green molecules. And so this law says that the vapor pressure, so the vapor pressure of a gas over a solution, so our is equal to, this is the mixing ratio of the gas over the solution, and multiply by we can think as a pure component vapor pressure. That is, in this case, the vapor pressure that this gas will have over a pure liquid water system. So we call this pure component vapor pressure. Depending what the spelling you choose. So if we now refer to this graphic, so here we have defined the vapor pressure in the pure system, the vapor pressure in this reference case, and here, based on this Raoult law, we have defined the vapor pressure over a solution using this reference value and the mixing ratio of the water vapor. And then we can link this definition to the relative humidity of the atmosphere. And so in an atmosphere with a given relative humidity, we can calculate the water mixing ratio that can be contained at equilibrium. Like it can contain an aqueous solution particles with this water mixing ratio. But then for aerosol, we have as well to remind us that we have introduced a solubility product when we introduce when we have started introducing some fundamentals of chemistry. We have seen, for example, a sea salt, so a solid one, it is diluted in a water solution, then it will be split in some ions, and the product of the molar concentration of these ions gives a solubility equilibrium constant. And by taking into account this solubility equilibrium constant, we then define for these aqueous solution particles, we can define the liquescence relative humidity. And why is important this the definition of this specific relative humidity is because it's kind of a threshold above which what happens is that you move from a dry particles to aqueous particles, where in fact you have that over this threshold the particle is growing because it's starting to absorbing water, and so you move as well from a dry to an aqueous particles. And so what happens is that you can move from this condition to this condition just because, well, if the particles is soluble into water, it can start to uptake the water, and so its size change, and so as well the scattering, the interaction with radiation change. And so you may move from what is called a clean day to a moderately polluted day. And why size matters? Why we refer to aerosol mainly based on their size, and we classify aerosol based on their size? Well, one reason we have already seen is because their toxicity change depending on their size and where they can be then stopped in the respiratory system. So here is the same kind of plot that we have discussed before about the position efficiency as a function of the size of the aerosols and given a different part of the respiratory system. Then one other reason is the light scattering, because the scattering is most efficient where the wavelength has a comparable dimension with the size of the particles. As well, the particle lifetime change with the size of the particle. Here we have the settling velocity given as a function of the size of the aerosols, and as you see, the larger the size, the faster is the settling, is the gravitational settling of the particle. And as well surface reactions, because if you consider the relative surface area, which is defined as the ratio between the surface and the volume of the particle, if we see this particle as some sphere, and if you compute the ratio between the surface of a sphere and volume of a sphere, you will get a ratio that is inversely proportional with the radius. So the smaller is the particles, the larger is this relative surface area, and so smaller particles provide relative surface area, and so they may trigger some surface reactions that, for example, are involved in the ozone chemistry. So here we have already mentioned, is just to show you that the scattering efficiency is maximum when the size is maximum when the particle radius is comparable to the wavelength of the incoming radiation, and so particles in the fine fraction scatter efficiently the incoming solar radiation in the visible fraction because of because the radiation can really interact with the element that is stopping its pathway. And for example, the fact of the scattering is then used to observe aerosols. Here I try to summarize the different way you can observe aerosols. So you may choose the resolution is not very good. I will try to improve later. So you may have two ways to measure aerosol. One is the horizontal view, for example, through solar occultation, that is measuring like the extinction of sunlight as the sunrise at the sunset, or the solar beam that has gone through atmospheric layer with the presence of aerosols. So solar occultation can provide good information about the vertical profile of the fraction of the atmosphere that you are looking at, but as a sparse sampling of the whole globe. Another way using an horizontal observation is a satellite that is sitting here. It can measure in two directions, the nadir just below the satellite, or the limb view on the horizon. And so this limb view can as well provide some information of the vertical profile, while with the nadir view is mainly a way for a vertical observation, and it won't provide you a vertical information on the vertical profile of the column, but it will mainly provide you an overall information of the column abundance of aerosols in the column that you are observing. So he may have this observation, the probe in this nadir observation, this nadir view observation, is that you can have a good horizontal resolution of the covering of the globe. And then you can also distinguish two systems. One is the passive and the other is the active system. So the active system is based to a laser pulse that is sent from the instrument, and so then the instrument just measures the signal back to the instrument. So it's active because the system is actually sending in a signal to measure the below atmosphere. And some example of this kind of satellite are, for example, Calypso, where if you look at observation from Calypso, you have really a good, you have a kind of a, how to say, like an horizontal plot where you have a good vertical profile of the atmosphere. And for example, if you have a specific plume of dust or smoke, you can really discriminate at which height the plume go up in the atmosphere. And so you may draw some conclusion about at which height this plume of aerosol has been then injected in the atmosphere. While, for example, in the passive system, you can't get this information about you can't get good information on the vertical profile you may have. Instead you can draw good info. You can get good information on the total column, atmospheric column. And why do we call passive system this? Is because they mainly work using this scattering process, the solar backscattering. So they are just measuring the solar radiation that has been scattered by aerosols. They are lingering in the atmosphere or other molecules, and as well the surface scattering. So at the very beginning, what was difficult was to discriminate the presence of aerosols on bright surfaces. And it's still difficult over, for example, desert area. We need to kind of initialize when we are retrieving the information from the aerosol, we have to provide already some information about the expected albedo of the below surface. So at the beginning, the best measurements have been done over ocean or over the area where the vegetation is very thick, and so you have a low albedo, and so you can then distinguish you can separate the scattering due to the surface from the scattering due to aerosols. Now the functioning of this passive system is improving. However, then depending on what you want to do, you may choose between some passive instruments. You may prefer one to another. Here, for example, we have MODIS and MICE. They are both passive. They both work with solar backscatter. But, for example, MODIS cover the globe twice a day. You have a MODIS observation in the morning and in the afternoon. So it's very good to cover, for example, if you want to see, if you want to study the seasonal cycle of aerosol over a region, you may want to choose MODIS because you have a well-covered, MODIS is well covering your area with good spatial and temporal resolution. Instead, MICE it takes 9 days to cover the globe. However, it provides a multi-angle view, so it provides a much sparser information. But for example, if mice just flew close to, for example, a fire that you want to study, it may provide you better information due to this multi-angle view. So then inside the family, for example, of, in this case, passive system, you may prefer one to another depending on what you want to study. So just to short break to put you on the same train as us, we are just discussing about aerosols. We have introduced what aerosol is, how aerosols are produced, what are the effects of aerosols, and as well how aerosol can be observed. Now we introduce four kind of aerosol: the sulfate, the nitrate, the carbonaceous, and the organic aerosols. I already mentioned that today's lecture is, I would say, a brief introduction on aerosol because the science on aerosol is very broad. So I'm trying to provide you the main information, but then if you want to delve into something, you have to go deeper into the literature, etc. So let's start introducing the sulfate and nitrate aerosol, and we will understand in a moment why we put them together, why they are so tightly linked. So sulfate aerosols are produced by our secondary aerosols because they are not just emitted in this way by like the mechanical action of wind. They are actually the result of a gas to particle conversion. So the gas phase precursor are mainly sulfur dioxide that is mainly produced by fossil fuel combustion or smeltering, and as well partly by volcanoes. And then we have the dimethyl sulfide among the natural sources of sulfur-containing gas. So that is mainly produced by marine plankton. Then these gases are then oxidized and converted to sulfate in the gas or in the liquid phase. Mainly in the troposphere, the aqueous phase is the preference one. They have a lifetime of less than around 5 days, and they belong to the fine fraction. Actually, sulfate are put in the range of scattering aerosols. And just this, I put this slide. We have already discussed this slide when we talk about the sulfur cycle, and it's just to remind you how from dimethyl sulfide or sulfur dioxide through the oxidation we transform this dimethyl sulfide to sulfur oxide, and then oxidation in an aqueous or in a gaseous phase move to sulfuric acid and then to sulfate. If we look at the global, the distribution of sulfur emission over the globe, here we have on the left the spatial distribution of anthropogenic emissions. So we see that since one of the main sources of sulfur dioxide is industrial activity, sulfur anthropogenic emissions are mainly located over highly industrialized area. And as well, what do you think is this trait? Most ships. Yeah, airplane, I think they don't have sulfur containing fuels, but I'm not sure. But I think that ships has a lot because coal, oil is contain sulfur, and so this is most ship tracks. And then for natural emission, why do you think is we have a hot spot here? So I learned this last year because there was a student that she was doing a PhD on oceanography and more on the like the biological system involved in the oceanography. And so here, these are the hotspots for nutrients in the ocean. And since one source of sulfur is the dimethyl sulfide that is released by phytoplankton. So since here we have some hotspot of nutrient, the phytoplankton is most efficient, and so here we have this also higher emission of natural sulfur. And the sulfate aerosols can, like they represent one of the main components of stratospheric aerosols. So in the stratosphere, between like 12 and 30 kilometers, we have a natural layer of aerosols. And the main part are small sulfuric acid droplets. The sources of these sulfuric acid droplets come partly from the oxidation of the carbonyl sulfide. So this carbonyl sulfide is a gas that once it is emitted is chemically inert, and it is water. It doesn't is water insoluble, so it can be transported up to the stratosphere, where it will be photodissociated by the action of photons and then transformed into sulfuric acid. Another fraction, another contribution to this layer of stratospheric aerosol comes from volcanoes. In fact, when you have a volcano eruption, you have a plume that has a strong vertical velocity, so eventually may reach the stratosphere, where you encounter an atmosphere that is it's dry, so precipitation is not a good loss process, and as well where layer transport, like also the mean wind speed is faster than in the troposphere, and so here what occurred is that the sulfur dioxide emitted by the volcanoes is transported directly up in the stratosphere. There is oxidized mainly by hydroxyl radical, because we are in a dry atmosphere. Is transforming in sulfuric acid, and then it may stay there even for a few years. It has been measured that aerosol associated to volcanic eruptions seated in the stratosphere even for 2 years. And they are involved in the chemistry of ozone in the stratosphere, mainly because if you remember, when we introduced the catalytic loss cycles for stratospheric ozone, we introduced the nitrogen oxide family, and we then introduced a larger family, the NOY, because to these nitrogen oxide radicals we had some reservoir species. As for example, the dinitrogen pentoxide. And so this dinitrogen pentoxide, when it reacts in a water solution, and it's not a good way to write the kind of reaction that I want to write, is to say that this dinitrogen pentoxide in an aqueous solution over a sulfate aerosol is then converting into nitric acid. So then we have seen this nitric acid and their role in polar stratospheric clouds. There are mainly clouds composed with nitric acid. So this reaction is an heterogeneous reaction that involves a gas, liquid, and is promoted over the surface of this sulfate aerosols. And what it does is that it consumes this reservoir of the NOY family to produce nitric acid. And so by consuming this reservoir of the NOY family, you then, the day after, you won't have any more the conversion of this reservoir back into the nitrogen dioxide. Then this nitrogen dioxide is involved, it will lead to the consumption of the chlorine oxide radical. So this chlorine oxide radical won't be consumed by the reaction with nitrogen dioxide. So what is important to keep in mind is that by consuming this reservoir of the NOI family, indirectly, this stratospheric aerosol are letting the amount, the concentration of this chlorine oxide increase, because they won't be consumed, their concentration will increase, and they are involved in a very efficient catalytic loss cycles of the ozone. So why I'm mentioning this? So the main things to bear in mind is that stratospheric aerosol may affect the chemistry of stratospheric ozone. And why I'm mentioning this is because if you look for geoengineering solutions, sometimes you may ended up with studies that suggest to put put sulfate aerosols in the atmosphere, because they will increase the scattering effect, and so they will reduce temperature. However, one of the concerns in doing this is the effect that this may have on the stratospheric chemistry of ozone, because of the indirectly increase in the amount of chlorine oxide radicals, although the emission of chlorine-containing gas hasn't changed. So now we move from the sulfate to the nitrate family, and we illustrate here how sulfate, nitrate are tightly linked. So here the story is that you have sulfuric acid that is mainly formed in the troposphere in an aqueous aerosol. So it dilutes in cloud droplets and forms sulfate. And in this aqueous aerosol, what happened is that ammonia, that you remember, ammonia NH3, is one of the main products of the biofixation that transform denitrogen into some reactive nitrogen. So ammonia is dissolved in the sulfate, in this aqueous aerosol, in the sulfate aerosol, because we have sulfuric acid, and we have an acidic structure, and we have a base, ammonia. And so what it does, ammonia dissolves in the sulfate aerosol to absorb the excess of acidity in this system, and it is absorbed till the acidity has been consumed. If there's some ammonia left, what will happen is that this ammonia can then go to absorb the excess of acidity related to the nitric acid, and to finally produce some nitrate. If there some ammonia left, and if we are under condition of low relative humidity, also what can happen is the direct interaction between ammonia and nitric acid to form an ammonium aerosol. So what you have to remember here is that the production of sulfate and nitrate is tightly linked, because they are both coming from the precursor of both are some acidic gas, sulfuric gas or nitric acid, sulfuric acid or nitric acid. You can imagine as a competition. They want both share. They want both can get the ammonia, because the ammonia is a base, will absorb the excess of acidity. However, most of the time, sulfate is winning in this competition. It's the first to have the ammonia that absorbs the excess of acidity, and so if some ammonia is left, then nitrate aerosol can be formed. So you understand here that the kind of environment in which these reactions are taking place also change the result, because if you are in an ammonia-rich environment, there will be the probability there will be some ammonia left are higher. Instead, if you are in an ammonia poor environment, then the kind of the most of the ammonia will be taken by the sulfate, by the sulfuric acid to form the sulfate. And then if other conditions change, for example, if you are in a condition of low relative humidity, what happens is then mainly you have dry particles, dry salt, and you have the possibility that as well the ammonia react directly with the nitric acid to form an ammonium aerosol. So you have even a third species. And then as well, the temperature can influence the functioning of this system, because if you look for example, the evolution of nitrate formation depending on temperature, you have that with lower temperature, the nitrate production is favored compared to higher temperature. So it's a complex system, but it's important to remember that they are connected, the production of sulfate and nitrate. And as well, they are connected to the abundance of some oxidant as hydroxyl radical, because hydroxyl radical is involved in the production of nitric acid, starting from nitrogen dioxide, and as well, hydroxyl radical influence the production of the oxidation of sulfur dioxide to produce sulfate. And so we finally, this is again to stress on the fact that the research on aerosol is very complicated, because you can't just follow the aerosols, you have as well to follow the atmospheric chemistry of the environment where you are, because you are not just focusing on some solid particles, you have as well to take into account their chemical composition and the chemical composition of the environment where you are. The interest on sulfate is still high, because although we have sulfur dioxide emission that reduced somewhere, for example, over Europe or over the contiguous US due to air quality policies, you have other places in the world where the emission of sulfur dioxide is increasing. Well, for example, for China, this happened like I would say 10 years ago, we observed this increasing in sulfur dioxide emission over China, while now they are also starting to they've also started to reduce their sulfur dioxide emission, while over some other area of the world we are observing an increase in sulfur dioxide emission. So still the science on sulfate is still at work, because there are still regions of the world where these aerosols can be produced. And then the nitrate, I haven't put the graphic, but we already discussed about the nitrate when we show nitrate and sulfate, what the position over the US. Nitrate is still, the interest on nitrate aerosol is still high, because we have as well an increase in ammonia emission, and so we are most shifting towards an ammonia-rich environment, and so the production of nitrate is more favored, because there's always an excess of ammonia left to produce nitrate. So now we have talked about the solvent and the nitrate aerosol. We introduced a new family of aerosols called the carbonaceous aerosols. And there we distinguish, under this family, we have the black carbon, then also include the elemental carbon and the organic material, that then we will say something more specific about organic aerosols. So black carbon is also called soot, and is mainly the product of incomplete combustion. So, for example, resulting from biomass burning, cooking or heating burning. Diesel is one of the sources of black carbon. Under the family of black carbon, we have as well elemental carbon, that is, and both are, they strongly absorb the visible solar radiation. They keep their basic form even at high temperature, so they are highly stable, and they are insoluble in water. And their lifetime is larger than, for example, compared to sulfate. Black carbon can stay in the atmosphere even for a few weeks. While the organic aerosol include some particles that are directly emitted. We will show some of them, and some others that are instead resulting from some gas to particle conversion. And one difficulty of this organic aerosol is that they include the large class of compounds. So here the complexity is even larger, because then you have to take into account really the composition of this aerosol. Carbonaceous aerosols are present all over the globe, and one of the main sources is, for example, biomass burning. And then the main source may change depending on the region of the world where you are. For example, here over the United States, we have a large fraction of organic carbon that is emitted, and instead the fossil fuel burning represent the main sources in terms of elemental carbon. If we look now at the spatial distribution of these black carbon emissions, we see the hotspot located over urban traffic is located, or where biomass burning is occurring, or as well coal, domestic heating. And what is interesting about the black carbon, among the carbonaceous aerosol, the black carbon we mentioned that is mainly insoluble into water, so it can be scavenged by rain. However, it can be removed from the atmosphere through a process called aging. So what happens is that we have the emission of black carbon that is hydrophobic, and this black carbon can go through an aging process, so it's really getting older. We can imagine this through some processes as coagulation and gas condensation. So the coagulation, the collision with other existing particles, or the condensation of gas on solid particles, and then it can transform into hydrophilic black carbon, where we have a particle of black carbon that has been coated by some other aerosols. There are instead water soluble, as for example sulfate and nitrate. And then at that point it can be scavenged, it can be removed from the atmosphere. And so in this way it can be, if this process is the one that dominates, it can be scavenged locally. Or otherwise, if this doesn't happen immediately, very fast, what happens is that this black carbon that is insoluble in water can be transported in the free troposphere, and there it can be transported even on a long range scale. And so the black carbon can then lead to transnational air pollution, transboundary air pollution. So for black carbon, the aging process is one process that can allow the scavenging through precipitation of this aerosol. Otherwise, the aging will take place higher in the stratosphere and in the troposphere, and then the removal of this aerosol will occur far away from the source of this aerosol. And among carbonaceous aerosols, we introduced the organic aerosols that not only they are very complex because they include a large amount of compounds, but they are everywhere in the world. So here you have the measure of aerosol components in the northern hemisphere, and at different location you have a pie chart that shows the fraction of sulfate, nitrate, and then the organic fraction, and the ammonium as well. And so if you look, the green fraction is the organic fraction, and you see that at different place in the world, you have always an important, quite significant, quite large fraction of the organic. Then it depends, of course, over the place where the measurement has been done, the fraction of this. For example, here over South America, you have a large fraction of these organic aerosols, while over Southeast Asia, the fraction is smaller and the sulfate dominate over the total. Or, for example, over Southern Africa, you don't have a big difference between a urban and a rural environment. So then it depends really on the place where you are measuring the aerosol composition. And among the organic aerosol, we have the so-called secondary organic aerosols, because in fact we have two kinds of aerosol, organic aerosol, the secondary and the primary aerosol. So the secondary aerosol results from the oxidation of volatile organic compounds emitted by plants. So we call this biogenic volatile organic compounds. These gases are then oxidized through reaction with, for example, hydroxyl radical, ozone, and they can lead to some oxidation product due to nucleation, so the gas molecule that then gather together, and so they can grow in size. Or another way to grow in size and produce some aerosol is the condensation of this gas molecule on pre-existing aerosols. And then depending on if we are in a gaseous or aqueous phase, then as well the representation into models, it will be different for volatile organic compounds. And above the family of organic aerosols, we have now we have included these primary biological aerosol particles that can be very large particles as pollen or plant debris. But we have as well this tiny fraction that involve bacteria, viruses, fungus, and so they have been added recently in the family of organic aerosols. However, still we don't know a lot about the kind of the emission of these primary biological aerosols, their reaction in the atmosphere, their role in the atmosphere. And for example, there's some increasing interest in using these primary biological aerosols for not greenhouse gas, geoengineering solutions. So they are also thinking about using this primary biological aerosol as a possible aerosol that will be released in the atmosphere. But still, if for sulfate aerosol we understood that they can have an effect on stratospheric ozone, we still need to understand how they could then react once emitted in an atmosphere where they don't belong to. So we don't know how they can react. So here you see in less than 40 minutes I presented aerosol. So it's really just a short introduction. It's more to show you how the different kind of aerosol that we distinguish today, their effect on climate, their effect on earth, how they form, etc. Now I want to spend a few minutes showing you, thinking about the interplay between climate and air quality, to show the connection that exists, and also show you that if you choose to study, or if you may end up to work on a topic related to atmospheric chemistry, biogeochemical cycles, still your background in meteorology is very important because they are strongly connected. And in fact, how can climate affect air quality? Well, firstly, the meteorology can change the way, for example, your polluted air mass can evolve. If you are in a well-ventilated boundary layer, you can imagine that the vertical mixing is very efficient, while if you have like a temperature inversion, this is limited, and so as well the dilution of your pollutant will be different, and so this can really change the air quality of the area that you are looking at. Then climate can change the emissions. We mentioned, for example, that the emission of volatile organic compounds from plants is, for example, connected with the temperature. If the temperature increases, then plants release more volatile organic compounds, apparently because for them it's a way to stabilize their, like the cell structure, and as well to protect themselves from thermal stress. But still, biologists are trying to understand if this is the only reason why with higher temperature plants emit more volatile organic compounds. Then this emission is also influenced by the availability of water for plants, and as well with drought and with increasing drought and temperature, wildfire can be becoming more and more frequent. And so changing climate can shift your emission towards like more chemical compound emitted by plants, by fire, etc. And as well, with an increase in temperature, in general, reaction rate increase. So as well, the chemistry can change with a change in temperature. And as well, today we mentioned for aerosol the relative humidity, as well the size of aerosols can change depending on the relative humidity of the environment where you are. And so to show you some example, here you have observation of ozone is the July mean over the Pennsylvania state, and July mean for temperature so ozone is the black line, temperature is the red line, and this measure has been done over a period of around 20 years. And as you see, the change in ozone really seems to follow the change in temperature. So a change in climate will influence air quality in an area. And as well, extreme events can change air quality. Here we are looking at the heat wave that happened in Europe in 2003. The main reason of this heat wave, of this extreme warm temperature, was due to a high pressure system sitting in the north of Europe that really induced some stagnant condition in terms of meteorology. And we now look at the change in the mixing ratio in the level of ozone and carbon monoxide. That we have seen are two important pollutants in the ground surface air quality. The yellow windows highlight the period where the heat wave occurred related to this high pressure system. And as you see, we have high level of ozone. Also, there were two waves. So I think that here, this one is probably the first heat wave, but I have to check. I'm just looking at this now. And then during this heat wave, there was as well a process, an episode of low pressure system that bring ventilation of the polluted air mass. And so you see that he eases the air pollution over the area. And during the same period, if we look during this 2003 heat wave, if we look now at the measure of emissions of concentration of biogenic volatile organic compounds, is the blue line, and we overlap this measure with the measure of temperature, the black line. If we look at the evolution over during August 2003 of these two variables, we see that with an increase of temperature, we as well an increase of the emission of biogenic volatile organic compounds, because plants will emit more of these compounds. And so in the IPCC report, you can find this kind of graphic that tries to really shows you all the connection between like climate and ozone. So how a change in climate can change temperature, water vapor, and can have an effect on ozone levels, and as well how climate can change emission of volatile organic compounds and methane, and how in the other way change, for example, in methane can change and then the radiative forcing. And if we then try to combine this information to try to think about how a solution to ease air pollution and to reduce and to mitigate climate change can be a win-win solution for both of them, for air quality and climate change, we can ended up with this kind of graphic where, so you have on the y-axis is the air quality, so moving up you move towards a better air quality, down toward a worse air quality. And on the x-axis you have climate change, so on the right, if we move on the right, we'll mitigate climate change, while on the moving on the left, we are moving towards a worse climate change. And here we see different like solutions. For example, sulfate reduction will be a win-lose solution. Why do you think we will have this outcome if we reduce sulfate aerosols? So it's a win solution for air quality, a lose solution for climate. So win solution for air quality is because sulfate can affect human health. And the lose solution for climate is because they are mainly scattering aerosols, so they reduce by reducing the amount of solar radiation that can reach the surface, they can also lead to a cooling effect at the surface. Instead, if we look at NOx, well, by reducing NOx, just the NO2 compound, this is a win solution for air quality, because we have seen that NOx are implicated in the ozone chemistry in the ground surface, while we have a neutral effect on climate change. Here, they are not including the nitrous oxide, N2O, which is instead a greenhouse gas. Instead, for methane, we have a win-win solution. Reducing methane is a win-win solution. Why? Yeah, it's a greenhouse gas. So by reducing methane, we are reducing the greenhouse gas effect that is added on top of the natural greenhouse gas effect by human activities.
I think we should say a small win-win solution.
A small win-win?
Yeah, because it has a very magnitude effect. Listen, this wind is so small.
Methane is so small, you say?
I mean,
that as compared to water vapor is small.
Yeah. Carbon dioxide.
Still, is that third or fourth?
It's
so
still,
you might do the fact with 0.1.
I don't know how much is strong, but one is there's a raising interest for methane as well, because it has a short lifetime. If you act on methane, it sits in the atmosphere for 10 years, while carbon dioxide, we still have to focus on reducing our carbon dioxide emissions, but they stay in the atmosphere for 100 years. So often we say that if we stop now to emit carbon dioxide emission, we still have a lot of emission that will stay, they are already in the atmosphere and will stay there for a long time. While if we reduce methane, the effect can be faster, because the lifetime is shorter. So then I don't know, it will be interesting to know, like to have a point from 0 to 10, how much is a win-win solution to reduce methane and doing something else. That is the, you see like sulfate reduction, for example, there's a stress on reducing sulfate emissions from ships, because also like ships are not part of all the negotiation that have been done about emissions during the COP event. Ships are not included in this budget of emissions. I don't know if it's like airplanes as well are not included, and I don't know it's because maybe the airplane is being built by France, but it's belong to a company that is American. So who is the country that is responsible of the emission of these airplanes? It's still difficult. So yeah, but this is just to say that sulfate reduction is also a challenge, because they are still not part of the negotiation that have been signed between countries. And if the decision is to reduce them, yeah, it's a good decision for air quality, but maybe we can, part of the climate warming that has been masked by sulfate aerosol will then appear. So this is the idea behind this win-win solution. Then the ranking of this solution, I don't know. Maybe there's somebody that's done that kind of study. And yeah, and then for CO2 reduction is a win solution for climate, but for air quality, I don't know what could be there.
Yeah, because for example, they are very important for plants production.
Yeah,
Plant
that's
production
true.
is important for human survival. And so if you kill all the CO2, how are plants going to survive, and how is man going to survive?
Yeah, but then the carbon dioxide is also emitted in methane oxidation. So there are natural processes. Sorry, go ahead.
I just said air quality does not concern the plants. I mean, it's about
about humans, but humans also depends on plants.
Yeah,
Plants
sure.
also depends on the CO2. It's very complicated.
Yeah.
No, yeah.
I saw it and I was thinking about it, and I'm like, it's very complicated, because if you kill it,
No, but that is.
CO2.
You only need to care about the extra input.
Okay.
Yeah, exactly.
Yeah.
So
Yeah.
that's
Natural
the
cycles.
idea, is what
Natural
we are
cycles
adding
are
up
okay.
on a natural system.
Yeah.
But still
That's
it's,
the anthropogenic one.
yeah, but still is, what you mentioned is important, is a complex system, what we try to represent into models and what we do care about.
Extension.
So yeah, and so just to I use your comment to also add two more slides where I try to show you as well how air quality can, for example, change the carbon cycle. We have already mentioned this about diffuse fertilization effect. Here in these studies, what the authors have done is they consider China, so they consider just regional air pollution, and they combine the effect of ground surface ozone and anthropogenic aerosols on the regional net primary productivity. So the net primary productivity is the photosynthesis minus the respiration of living organisms. And what they have observed is that the effect of this, an increase in sulfate in ground surface ozone and an increase like the effect of the current of the present day surface ozone and the present day anthropogenic aerosol over this region, over China, has led to a decrease of the net primary productivity. And this because you have to combine all these effects. So we have discussed that the presence of aerosol may trigger some photosynthesis related to the shaded leaves. So the aerosol direct effect may enhance the net primary productivity due to the diffuse radiation fertilization. Then they account for the indirect effect of aerosol that lead to a reduction in precipitation, and so this has an effect as well on the plant functioning. And then we have ozone. When ozone is uptake by plants, plants can uptake ozone up to a certain threshold. So this is good because plants also act as a kind of a cleaner of the air that we breathe. However, above this threshold, you start observing this yellow-brown spot over a leaf. It's kind of a burning of the leaves. And so above this threshold of ozone that can be uptaken by plants, well, the plants, due to this ozone damage, the plant is less efficient in performing photosynthesis, and so ozone damage finally reduce the net primary productivity. And by taking into account all these effects, what has been observed is a reduction of around 10–15% of the total net primary productivity over the region of China. This is as well to put in this complex system not just human beings, but as well plants that then have a role, for example, as we mentioned, in maintaining, like uptaking pollutants, and as well in providing oxygen through the process of photosynthesis. And then one other example of the connection between like plants and air quality is, for example, and in the case of land cover change, is the case of oil palm plantation in Southeast Asia. So in this area, what is happening is that the native forest, so that here is, I can't see very well, but it should be the, so yeah, I also linked to the observation. So the native forest here is the green area, the native rainforest that exists here in Malaysia, while the white area is the oil palm plantation. And the dot that you see over shows the mixing ratio of isoprene, that is one of the main compounds in the family of biogenic volatile organic compounds. And what has been observed is that isoprene emissions are much larger over oil palm plantation, because the plants that there are this kind of cropland, this plantation, the plants that are introduced there have a large isoprene emission potential compared to the native rainforest, to the primitive rainforest. Actually, they have a potential that is 5–10 times higher than the primitive forest. So then the question of the authors of this study is, okay, what will be the effect of shifting really the background environment in this area? Because by adding oil palm plantation, we are increasing the amount of these biogenic volatile organic compounds in this area. We are really moving the levels towards higher concentration of these volatile organic compounds. They are involved in the chemistry of ground surface ozone. If you remember the recipe to produce ground surface ozone, we have EOC plus NOx plus sunlight, and this lead to ground surface ozone. So we are increasing this, and as well, together with oil palm plantation, what happened is that as well there's the area is changing because we start introducing more transport, more industries. Also, the NOx concentration may vary. And so here what they show is the mixing ration of ozone as a function of mixing ration of nitrogen oxide, NOx. And they have two scenarios. One is then with in a rainforest landscape, so in a native landscape, and in a plantation landscape. So a scenario where the rainforest will still be there, and a scenario in which oil palm plantation will be increased. And so now we are around these levels of nitrogen oxide and ozone. So these have been measured in the rainforest and over plantation area. And if we just, by shifting both the NOx and the VOC emission, we may end up with a large amount of ozone production, because if we are shifting the NOx emission in a natural landscape, you see we will stay below this air quality standard level, is a threshold that has been an air quality standard that has been defined by the World Health Organization. Instead, if we increase the NOx mixing ratio, the NOx concentration in an oil palm, under an oil palm plantation scenario, you see that we may pass this threshold if we follow the red line. So what has been by using some modeling, the authors conclude that just a small increase in the NOx level may lead to levels of surface ozone that may exceed the air quality standard of 50 ppb, above which the effect of ozone on plants and on human beings will be above that. Ozone is toxic for human beings and plants. And this value of nitrogen oxide, by increasing nitrogen oxide and bringing to few ppbs, these levels are levels that are observed, that are measured in Europe in rural areas. So why they will have this large effect on ozone is because at the same time you are changing the emission of volatile organic compounds.
Wait, you said they are measured in rural areas in Europe?
Like it's to compare, so now the area is as this value of nitrogen oxide and ozone. If now in the next years the levels of nitrogen oxide will increase of few ppb, the ozone could exceed this threshold, and the NOx level to have this high ozone will be just comparable to the NOx levels that occur in Europe in rural areas. So it won't be such a high levels of nitrogen oxide compounds. It's just that they will be emitted in an area where human activities, land cover change induced by humans, has changed as well the amount of volatile organic compounds. So this is to stress on the fact that when you look at, we are already thinking about this when we discussed about the chemistry of ozone at the surface. We have mentioned that we have to take into account in which regime we are, in a box-limited regime or in a NOx-limited regime, but still, even if we are most of the time in a NOx-limited regime, we see with the ozone production efficiency that still the amount of volatile organic compounds is important, and so it's really a strong nonlinear system. And so these were just two examples to show you how finally everything is really interconnected.